We are here, right? Yeah. So now we are here. Almost there. The equation. Yeah. My remote control. Yeah, here. All right. All right. Oh, what's wrong? Oh, remote control should be connected to my laptop, not the station. Here. Laptop. Oh, laptop. Yeah. Receiver. Yeah, I need to use adapter because the USB type is different. I need to use some adapter. Some adapter. Oh, I remember I have some adapter. Remember, I see it. I see it. Yeah. Oh. All right. So remote control. Yeah. Let me, use my hand to do it. Yeah. Yeah. Next time I will fix it. Yeah. All right. Yeah. Let me just do this way. Yeah. This way. Okay. All right. Yeah. So the final equation. So we have it. Final equation. All right. But that final equation, do you think you can solve it? Can you solve this equation? Do you know how to solve this equation? What factor? Oh, yeah. You know more. We haven't been there. Yeah. Separable, right? Separable. Yeah. Can you do that? Separable. All right. So here, oh, I couldn't use this. Sorry. Yeah. Here. Yeah. With initial value 0. So I leave it as practice. You complete the solution. Okay? Yeah. You just complete the solution. Yeah. Answer?
Yeah, like the
answer
to what was the temperature inside the building. That's exactly.
The function?
No, just like the solution. Yeah, like the
solution? Oh, solution? Practice. This one from textbook. Yeah. So solution answer all from textbook. Yeah. All right. Yeah. The detail you can find from textbook. Okay. All right. Move to next question. Problem number 6, leaking tank. This one, we need to use differentials to do the modeling, okay? Try to get used to it. How to use differentials to do analysis. This tank, okay, there is a hole at the bottom, okay? So water leaking out, yeah? Little hole. It's a big tank, yeah? So now we need to look at the question. It concerns the outflow of water from a cylinder tank with a hole at the bottom. Yeah. Then you are asked to find the height of the water in the tank at any time if the tank has diameter 2m, the hole has diameter 1 cm. Yeah. And the initial height of the water when the hole is opened is 2.25 meter. Yeah. When will the tank be empty? Yeah, that's the question. Yeah. After how many hours? Yeah, so after you open that hole at the bottom, you clock it. then after how many hours the whole tank is empty. So here we need to solve this problem. Okay, yeah. We need to do modeling. When we do modeling, some law should be used, right? Yeah, usually some physical law should be used. Yeah, here. So first, we need to understand the problem first. Yeah. All right. Modeling. Torricelli law. Okay? Torricelli law. Some special law. Okay? Yeah. Torricelli law. Yeah. So what's that? Yeah. The formula given this one. V, little v, velocity. V of t, velocity. Okay? Yeah. And time t, velocity. Because the water flows out with some velocity, right? Velocity. How many meters per second? Velocity. Okay? Yeah. If the velocity is large, then leaking faster, right? V of t. So Torricelli's law told us the velocity equals 0.600 square root of 2g h of t. H, height. Look at the height function. The height of the water, it's a function of t, height function. Okay, g. So you know the g, right? That gravity constant. Yeah, here given here. Yeah, g is the acceleration of gravity at the surface of the Earth. G equals 980 centimeter per second square, or 32.17 feet per second square. Yeah, centimeter you can convert to meter, right? So here there are different units. Some places we use meters, some places we use centimeter. Centimeter there, also centimeter here. But we need to do conversion, right? You cannot mix centimeters and meters. We need to convert to meters. Yeah. All right. Yeah. What is the relationship between V of t and H prime of t? So here, the key. So first, in this modeling step, from the Torricelli's law, you have equation between velocity function and height function, right? Two different functions. So we cannot solve. In one equation, we have two different functions. So we want to find the relation between the velocity and H prime, derivative of H. If we can find it, then we can get rid of the velocity, right? If we replace the velocity by an expression of H prime, then we have a differential equation, right? Yeah. So the first thing we need to do, we need to find a relation between V of t and H prime of t. Okay. The rate of change of height, height changes. Okay. When the water leaking out of the tank, the height is reduced at some rate, right? Yeah. The rate is a function of t. It can change. Rate of change, derivative changing with the function with the time t. Yeah. But we need to find that relationship. If you get it, then you're done. Okay? You can solve it. Yeah. All right. Here, we need to use the differential concept. So here, let me show you how to use the differential concept. When you use the differential concept, you start with the delta concept first. Then you take the limit. You get a differential, right? So we use the delta change notation first. Yeah. All right. At any t, when the water flows out, what is changing? Can you see what is changing? What quantity is changing? Water level, yeah. Water level, in what specific quantity? Yeah, water level, do you want to use the height? Height represent the water level. Yeah, height, water level, yeah. But here, when you, remember, when you establish an equation, you need to find some quantity equals another quantity. You need to find that equality. Okay? Equality. Can you see something that gives you some equal information, equality information? Can you see from this whole picture, anything gives you some equality information? Right? Yeah. Think about water flowing out. How do you measure the amount of water? Amount of water flowing out. How do you measure that? There should be a way to measure water flowing out, right? Certain amount, okay? Water flowing out, certain amount. Suppose you have representation for that amount. After you take away that amount, how do you measure the amount of height lower down in the tank? In other words, how do you measure the volume of the water in the tank is reduced? How much volume is reduced? Can you think about that equality? The volume reduced equals the volume of the water flows out. How about that? That equality. Water volume reduced, that's amount of water, right? A certain amount of water reflects the water volume, water amount reduced in the tank. Okay? Then water flows out. Can you measure amount of water flows out? Yeah. With the velocity, you know the velocity. Okay? You know the velocity. Each second, the velocity times t equals the distance, right? Velocity times t equals the distance. Distance, all right? Yeah, let me draw something here. Yeah. Yeah. Velocity, yeah. Suppose here we're talking about the hole at the bottom. Water flows out, right? So here, the water flows out. Okay? Yeah. Let me get a better one. Yeah, this is not that good. Where? Oh, behind it. Yeah, okay, good. All right. Yeah. So let me, the hole at the bottom, yeah, much better. So water flows out, okay, with velocity v of t, okay? Yeah. Do you want to represent the distance? Water flowing out, okay? Yeah? All right. So v of t times time t, or delta t, right? Because when you flow out in a small amount of time, so use delta t, right? Use delta t to measure this distance. Okay? The distance, the length, you know the area, right? Can you calculate the volume? You have the length, the height, you have the bottom surface. Can you calculate the volume of the water? Right? This much volume. And in the tank, the volume reduction, that amount, can you equalize those two amounts? Think about that. Okay? That's the equation we want to establish. Yeah. Let me show you the detail. Here, all right. Equality. Volume change. This volume means the tank, water in the tank volume change, equals the volume of the water flowed out. Yeah, there is another volume, right? Water flowed out. So we use another expression for water flow out. In tank, that volume change, a different expression, right? Yeah, two different expressions for the same quantity. So we get equation. Yeah. With this equality, now our next thing, use math formula to represent each term. Okay? Yeah. Volume changed. What is volume changed? Volume change. Pi r squared. Oh, yeah. Cylinder volume, pi r squared. H difference, right? Yeah, H difference. Yeah. Here, the volume change, we use delta V. Delta V. Okay? Yeah. Delta V. Yeah. Now, before we do that, let's write diameter, capital D. That's the tank diameter. Okay? All right. Then the radius equals 1 meter. Radius. Then little hole, little d diameter 1 centimeter, and little radius 0.005 meter. Yeah. We need to use the same unit. Okay? All right. Now, the equation. Delta V, volume change, that's delta V. Okay? What's delta V? Next step, we will do the delta V explicit representation. All right? Explicit pi r, capital R squared, delta H. Okay? Yeah. Then, left-hand side, right-hand side. Yeah. Yeah, so yeah, we will see that. Yeah, because delta H decreases. Yeah. So we will use that information later, decrease information. All right. The right-hand side, volume flowed out, volume, the little hole area, pi little r squared, right? Yeah, little hole area, all right? Velocity times delta V. Velocity times delta V. That length. After delta t time, yeah, time change, delta t, so that water moves that much distance, v delta t distance. Okay? We treat it as a height of the cylinder, right? This shape also a cylinder, little cylinder shape, right? So the height of the cylinder multiplies the bottom surface area. Okay? Yeah. So the right hand side, pi little r squared, velocity function of t times little t. How about that? So these two quantities should be the same. Should be the same. So we get an equation. We get equation. Okay? Yeah? All right. Then we do simplification on this equation. Yeah. Pi cancel out. Okay? Pi cancel out. Delta H, delta V, delta H over delta T, one side, yeah, this side delta H, so we divide delta T, okay? Then capital R squared, do division, so we get left-hand side. Why negative? Negative because our height decreases, okay? The height decreases, we use negative derivative. If the height increases, we use a positive derivative. How about that? Positive. Okay? Or the volume change, because volume decreases, so it should be negative. If the volume increases, it should be positive. Okay? Yeah. So here the volume decreases. Yeah. So we use negative. Yeah. All right. So now delta H over delta T equals this equation. Then take the limit. Delta T goes to 0. We take the limit. So we get derivative, right? Yeah. Here we do not need to use differential. Yeah. But we use delta. Small change amount. Small change amount. When you do modeling, yeah, in this situation, you need to use delta. Small amount. Okay? Get used to equation setup. Yeah. All right. Now we can write our final equation after we take the limit. Yeah. dH over dt, or you can write H prime, right? H prime, yeah, equals this expression. Okay? Yeah. That expression, the V, so you have the relationship between H prime and the V. Can you write V as an expression of H prime so you can go back to the, Torricelli's equality, and we get a differential equation about H function. That we can solve. Right. So another step, all right, yeah, here, yeah, we just plug in some number, yeah, because there is some, yeah, oh, here also, yeah, here, right, we replace V, yeah, here, even simpler, we replace V by this H expression, okay? Then after some simplification, we get this expression, okay? Yeah, that expression with initial condition. Okay? Yeah. So little r, capital R, G, all known. Yeah. H function to be solved. Do you know how to solve it? Can you see the structure so we can solve it? Some special structure. Separable. Can you see the separable structure? Yeah. So leave it to you. Yeah. Solve it. Yeah. Yeah. Same as the previous question, answer, solution, all in the textbook. Okay? Yeah. So you can use, the details in the textbook. Yeah. Yeah. Try to understand. Okay? Try to understand. Yeah. Yeah. If you feel hard, you can let me know so I can talk about in class. Okay? So I'm thinking about problem, because last time a few students asked me to give the computation details. So if you need, so I may do some computation details. Everyone, you can calculate the basic derivatives and integrals. So you need to make sure all these computations you can handle. Yeah. You need to make sure, okay? Yeah. Yeah. In my solution to those exercise questions, I'll give you the details, okay? So you just study. So if you feel hard to understand, let me know, okay? But you need to ask yourselves, you can do the same thing after you study. You can do the same thing. Okay? Yeah. All right. Yeah. So let's move to the next question. Extended separable ODEs. Yeah. So here we try to extend our separable technique a little more to get an extended method, reduction to separable form. That is, here from the title you can see, at the beginning, it's not separable. At the beginning, if you really want to use the separable method on it directly, you cannot. Yeah. But after you do some conversion, after you do some variable substitution, then you make it separable. Yeah. In this way, we can extend our separable technique to cover more cases. Yeah. So let's recall. Oh, why going so fast? Yeah. Let's recall. We consider this new form. Okay. Inside the function, you have y over x structure. That structure. Yeah. First, in general, this one it's not separable, right? Yeah. X and y inside function parentheses. How can you separate x and y? Think about that. How can you separate x and y? Yeah. Here, I'll give you a simple example. In that example, can you separate x and y? Nobody can do it, right? Yeah. But because the structure is so special, y over x so special, now we introduce a new variable. We can make it separable. Yeah. Yeah. So it's not, yeah. So the function f could be very complicated. Yeah. Because in this general case, that little f function could be very complicated. Okay? Yeah. So here we want to do some method that it does not rely on that little f function. No matter how complicated that function is, we can always apply this method. That's the goal. Okay? Yeah. So here we introduce a new variable for that y over x structure. So let u be y over x. New variable u. Okay? Yeah. After that, inside f, only one variable. Before we use the new variable inside function, you have two variables. But after we replace that structure, y over x, by a new variable, we make a single variable inside f function. How about it? How good it is? Much simpler, right? Yeah, this time much simpler. Yeah. All right. So we can represent y prime equals f of u. F of u. Yeah. All right. But what's the relationship between y and u? Yeah. Here we want to represent y prime in terms of u and the variable x. X is still the variable. X is still the variable. So we still need to keep x inside the equation, but we want to replace y by u. In our final equation, we don't want to see y. We want to see an equation involving x and u equation. Yeah. So look at that new equation. Now we know y equals u times x. Can we take y prime on u times x? Okay? By the product rule of derivative. You know the product rule, right? So here you have a product. We take derivative on this product. So by the product rule of derivative, we can write y prime equals u prime times x plus u. U times x prime. X prime is 1, right? X prime is 1. Okay? So u prime times x plus u times x prime, but the x prime is 1. So we get u. Okay? Yeah. Now you should replace the y prime in the original equation by this expression, u prime x plus u. Okay? Yeah. Yeah. So let's go back to, we update the form. This time we use u prime times x plus u equals fu. After the change, can you see the separable structure in the new equation? Separable structure. Can you see the separable structure? Okay, the separable. Put all u terms at the one side of the equality, x related terms the other side of the equality. Can you do that? Yeah. Yeah. It should be easy, right? Yeah. Separate u and x. How about this? This way. Can you see this way? Can you do the algebra? Get this expression. Left-hand side, right-hand side of the equality in this way. After that, do the integral. Do the integrals. Yeah. Right-hand side easy, right? Left-hand side depends on how hard is that f function. Okay? Yeah. Hopefully it's not too hard, so you can do it. Okay? Yeah. Yeah. Solve this as an example. So let's solve this equation. Okay? Yeah. Yeah. Apply our new method, variable substitution. After the variable substitution, yeah, so we jump a few steps. Yeah. Or we can use you can treat this as a formula. How about that? Okay? When you have that form, can you use this as a formula? Right? Because you know the f function, right? You know the f function. Yeah. So you just use your new f function there. Okay? Yeah. Plug in the formula. Okay? You do not need to give me all the intermediates. You do not have to. Okay? Yeah. In your homework assignment test, if the formula is available, just use it. Okay? No. We derive the formula, then we do not have to derive it again, right? In your homework assignment tests. Use it. Question? Mm-hmm.
When you go to the bottom, you're solving the original function, the sine of y, right? Where did the minus u go at the bottom equation?
Minus u. Remember this sine u plus u. This plus u minus u cancel out. So it's gone. Okay? Cancel out. It's gone. Yeah? It's simpler. Simpler. If it cannot be canceled out, then it's very hard. Then it's very hard. Yeah. So we like it. Yeah. We want to cancel out. Yeah. We like it. Yeah. All right. Yeah. All right. So here, let me ask you another question. Yeah. So we finish this type. Okay. So when you see the structure of that, so you should have some confidence to solve it. Okay. All right. Now, I ask you, how about this form? When you see the form like this, here the k is a constant. Can you use the similar way to solve equation like that? K is a constant. Yeah. So I can put a different constant number for k. Yeah. Yeah. So you can use the same idea to do it, right? Yeah. So here you can see, yeah, when you have some new method, you need to try to try to use that idea in many different cases. Yeah. Yeah. All right. Yeah. Yeah. So we will. Yeah. Yeah. So we will. Yeah. Soon. Yeah. Here. Yeah. I will finish soon. Here, I try to work on 2 questions, but this time you can see, this time, y plus 4x. Look at that. Y plus 4x. So sometimes in the given equation, you may not see how do you do the correct substitution, right? Sometimes you may not see clearly. So you need to do some formula transformation. Then you can apply our standard way substitution. Standard way. Yeah. But before you do the formula transformation, you may not see it clearly sometimes. Yeah. The first one also. First one, you couldn't see y over x structure, right? There is no y over x structure. Yeah. But you can write y prime equals, a fraction form. After simplification, you can get a y over x structure. Yeah. After that, you can get a y over x structure. Yeah. Yeah. All right. Yeah. So I leave next time. So here you can see I haven't finished part B. Yeah, just barely part B. Yeah, finished. Yeah. Anyway, for our module 1, although I go slow, but I try to build a solid foundation for you. Okay. Yeah. So you have to do well at the beginning. Yeah. Otherwise, if you cannot follow, then the remaining of the semester it will be very hard. So I want to make sure everybody can follow for module 1. Okay? Yeah.